Today we will talk about Bayesian. So the Bayesian based on the Bayes theorems, which is the probability of the hypothesis H depend given the dataset D is equal to probability of D given H multiplied by P of H divided by P of D. So which will result in the chosen hypothesis will be the one that has the maximum value of pH given D. So for real value, the Bayes theorems will become like the minimized sum of square errors, which the chosen hypothesis will be the one that minimizes the difference between D and H of Y, that's square. And then we have the function for classifier, which is the P of Vg given He multiplied by P of Hi given D. Vg is like the version value in the version space. For example, for classification, Vg will contain two values, 1 or 0, or choose yes and no. So the naive Bayes will given a assumptions that all variables are independent, which means the joint probability of A1 to AN given Vg will equal to the product of PAY given Vg. Then the function for classifier turns out to be the maxima of the estimated probability of Vg multiplied by the product of the probability AY given Vg. So this makes it much easier to compute the function because it's easy to calculate the product P of AY given Vg than calculate the joint probability of P A1 to AN given Vg. And when none of the training instances of the target value have the attribute, we will modify the formula that we will add the some constant m, p, and m. The p will be the overall probability of the Vg, and m will be a constant that we choose. That will avoid the probability of a y given Vg equals 0, because that probability will be one in the product of the function of the classifier. Therefore, if it equals 0, the whole function will equal 0, which make we lost that information and usually will produce a incorrect prediction. So we have the Bayes network. If all the variables is not independent, we cannot use the naive Bayes. Therefore, we have a network that represent a set of conditional independence assertions. Each node is conditionally independent of its non-descendant given its parents. So conditional independence is that if we have three variables x, y, and z, if the x is independent of y given z, then we say that x is conditionally independent of y given z. Formally, we have the p of x given y and z equal to p of x given z. Then the joint probability of all the variables ey to en will now be equal to the products of p ey given only the parents of ey. This will reduce the number of probability we need, since we only account for the parents of the variable we want to calculate. Previously, in the normal optimized Bayes classifier, we need to calculate the joint probability of all of the variables. But now we only need the joint probability of some variables, the only variables that relate to each other that we need. So if it's independent, we don't need to calculate the joint probability of those two, and that will reduce the computational cost of the Bayes. So in conclusion, first, the Bayes classifier is based on the assumption that the quantities of interest are governed by probability distributions, and that optimal decisions can be made by reasoning about these probabilities together with observed data. It is important to machine learning because it provides a quantitative approach to weighting the evidence supporting alternative hypotheses, and the Bayesian reasoning provides the basis of learning algorithms that directly manipulate probabilities, as well as a framework for analyzing the operations of other algorithms that do not explicitly manipulate probabilities. So each observed training can be decrease or increase the estimated probability, and this provides a more flexible approach to learning the algorithms that completely eliminate a hypothesis if it's not found to be inconsistent with any single example. And we can also apply prior knowledge to strengthen the prediction, and the Bayesian methods can accommodate hypotheses that make probabilistic prediction, and the new instance can be classified by combining the prediction of multiple hypotheses, not just one. And even in case where Bayesian methods prove computationally intraceable, they can provide a standard of optimal decision making against which other practical methods can be measured. However, it has some difficulty. The first one is it requires initial knowledge of many probabilities. So when these probabilities are not known in advance, they are often estimated based on background knowledge, previous available data, and assumption about the form of the underlying distribution. This can prove to be untrustworthy and can harm rather than strengthen the predictions if we not carefully calculate the prior knowledge. So, secondly, the significant computational cost required to determine the Bayes optimal hypothesis in general case. In certain specialized situations, this computational cost can be significantly reduced. So we have the naive Bayes that reduce significantly the computational cost by adding the assumption of independence. We also have the GIFs algorithms that only choose like a subset of all hypotheses based on a certain function that can reduce significantly the cost of computations. And that's just two of the way that we can reduce the computational cost.